Okay, we can finish chapter 6 today. Then we turn to study chapter 7. Chapter 7 is about numerical computation of derivatives and integrals. So far, we have used polynomial to do interpolation, but actually, we can use other functions to do interpolation. Today, let me present one example. In this example, I use other functions to do interpolation. Suppose we are given a table of points on the XY plane, points on the XY plane. Suppose the lots satisfy these inequalities: T0 less than T1, less than T2, and so on, less than Tn, Tn less than B, T0 greater than A. So all the lots are in the interval from A to B, Now, I want to find the following spline functions. We seek a function. Let me give a name, T of X, such that the following properties are satisfied. Function T is in this space. Function T is defined on the interval A to B and has second derivative, first derivative. They are all continuous. B, function T interpolate this table. Beta 0, beta 1, beta 2. The betas are not function values, just points on the XY plane. B, T, the value at Tk is equal to Bk. K between 0 and N. C, on each of the following intervals. The first interval from A to T1, T1 to T2, and so on. Tn minus 2, Tn minus 1. Then the last interval is Tn minus 1 to B. Over each of these intervals, T satisfies the following differential equation. T take derivative 4 times minus tau some number, tau square T second derivative is equal to 0. Okay. So over each interval, T may not be a polynomial this time. Okay, T satisfies this equation. Okay. Let me make a remark about this differential equation. Let me call this differential equation equation 1. Remark about equation 1. When there were two extreme cases, when tau is 0, when tau is 0, then 1 is t, take derivative 4 times is 0. Now solve this equation by taking integral, right? Solve it, take integral once, then we get derivative 3 times is equal to a constant, right? Then take derivative again. We get tx plus a second constant. Take integral again, 1/2 cx squared plus dx plus e. E is a constant. Then take integral again. So the function satisfy this equation is a cubic polynomial. 6 cx to the third plus 1/2 dx squared plus ex. Say f. Don't use f. F usually refer to a function. Say a, right? Constant. So a, c, d, e, constants. So the solution of this equation corresponding to tau is 0. The solution is a cubic polynomial. This is an extreme case. A second extreme case is when tau is infinity. Then 1 is, let me divide the equation by tau before. Tau is infinity. Say tau is a very large number, then I divide the equation by tau squared. Now let tau approach infinity, then tau approaches infinity, then this differential equation becomes, the first term approaches 0. So this differential equation is this. Now solve this differential equation. We see that take integral once, constant, then take integral again, cx plus d. So when tau is infinity, the solution of this differential equation is a linear function, a polynomial of degree 1. So tau here, we interpolate tau as a force, When the force is small, tau, the graph, is nearly about the graph of a cubic polynomial. When the force is large, then the graph of tau is nearly a line. So tau is a force. When the force is large, the force stretches the graph tightly, right? Make the graph as near as a line when the force is large. So because of this, we call this parameter a tensor. When the tension is small, the graph is about a curve of cubic polynomial. When the force is large, about a line, right? Tighten the curve. Okay. So this interpolation, the function, we call it tension spline function. Spline function. Tension. T is a spline function. Tension spline. Okay, tension spline. T, of course, satisfy these conditions. Now, let me solve this differential equation. Solve this differential equation and determine the tension spline function T over the interval from T0 to Tn. Actually, this is the interval that we are interested. Yeah. Okay. Now, how to solve this problem? Okay. Similar to the case of constructing cubic spline. Okay. We let tau at this point unknown. Second derivative at the length, say Tk, is equal to Ck. What is Ck? Will be determined. I don't know yet. K between 0 and n. 0 and n. Okay. Right. Then over each interval from Tk to Tk plus 1, right? Yeah, over each interval, by definition of T, over each interval, T satisfies this differential equation. So T, the differential equation is derivative 4 times minus tau square. T second derivative is 0. And at the two boundaries, at the two endpoints, T at Tk is equal to Ck. T at Tk plus 1 is equal to Ck plus 1. So on each interval T, the tension spline satisfies this boundary value differential equation. Differential equation. Now, from a course about ODE, ordinary differential equation, the solution to this problem is the solution. The solution is a T of x. Of course, x is in this interval. Is equal to Ck. We don't know Ck yet. Okay. Then times sine. This is a hyperbolic function. The definition of sine, SINH, x, hyperbolic function. It is a EX minus E negative x over 2. It is not a polynomial this time. Okay. sine of tau times tk plus 1 below tk plus 1, we are given it is a lot minus x. Okay. Then plus ck plus 1. We don't know ck plus 1 yet. Then times sine. How about let me use square brackets here. Square brackets. Yeah. Okay. Square brackets. Tau times x minus tk over tau square sine h tau times hk. What is hk? Hk, we mean this number, tk plus 1 minus tk. The difference of the adjacent lots. Then plus beta k. What is beta k? Beta k here. Also here, beta k is given to us below beta k. Minus ck, we don't know, over tau square times tk plus 1 minus x, then over hk. Definition is here. Plus beta k plus 1 below beta minus ck plus 1 over tau below tau times x minus tk over hk. This is the solution to this boundary value differential equation. So over this interval, the tension spline is this function, log a polynomial, log a polynomial. Okay, now how to determine CK? How to determine CK? Recall that T we assume is in this set. Up to this point, we have used the continuity of T second derivative, because when second derivative at Tk is equal to Ck, yeah, these conditions implies the continuity of second derivative. And also we have used the continuity of T. Why? Because we assume the value of T at the lots Tk is beta k. When Tk satisfies these conditions, Tk is continuous at the lots Tk. So actually, up to this point, we have used the continuities of T and T second derivative. What we haven't used is the continuity of the first derivative. Now, let me use the continuity of the first derivative to determine Ck. Okay. Okay. Because T is continuous and over the interval AB on AB. So in interior lots, we should have T x when x approaches TK from the left side should be equal to the limit as x approaches TK from the right side. Continuous at the lots where K is 1, 2, and n minus 1. At T0, T, derivative of T, automatically continuous. At Tn, also automatically continuous. The problem may occur at interior lots. So because derivative of T continuous, so we should have this equation at interior lots. Now, go back to this function. Go back to this function. This function is defined from TK plus 1. Now, I let x approaches TK from the right side, from the right side. From TK to TK plus 1, this portion of the function T, let me denote it by TK. And from TK minus 1 to TK, this portion, let me denote it by TK minus 1. So actually, this is TK at TK is equal to TK minus 1 at TK. Yeah. Okay, now how to get TK minus 1? Replace the K here, with K minus 1. Then we get TK minus 1. Then plug in the lot TK in X. We get the left side. And then plug in TK in the X here. Then we get the right side. Now simplify this equation and rearrange the terms. Then we have the following equation. AK minus 1, some number. What is A? Yeah, A is here. AK. AK is 1 over HK minus tau sine tau HK. This is AK definition. CK minus 1. We don't know CK minus 1. And then plus BK minus 1 plus BK. What is BK? Yeah, BK is this number. Tau cosine T HK. Yeah, cosine here is a second hyperbolic function. Then over sine tau HK minus 1 HK. This is a BK. BK times CK. And then plus AK times CK plus 1 is equal to CK minus ck minus 1. Where ck definition is this number. This number. Beta, below beta. Beta, the points on xy plane, they are given to us. Minus beta k, then over hk. Yeah. Okay. So recall that k is from 1, 2 to n minus 1. Yeah, k is 1, 2 to n minus 1. Yeah, this equation is from the continuity of the first derivative of t, right? At the interior lines. How many equations? N minus 1 equations. How many unknowns? Unknowns. How many unknowns? C0 unknown. Yeah, plug in 1 in K. You see the first term, C0. C1 unknown. Cn minus 1 unknown. If I plug in n minus 1 here for K, then I get Cn. So Cn unknown. N minus 1 equations. N plus 1 unknowns. We have 2 freedoms. We can freely assign values to, say, C0 and Cn. Just like in lateral cubic spline, we usually set C0. What is C0? We call that second derivative of t at t0. Usually we set it to 0, but you can assign any number. Cn is second derivative at tn. Tn, usually set it to 0. Then from this, then we have n minus 1 equations and n minus 1 unknowns. So solve these linear systems. Solve this linear system. We get all the unknowns, all the C's. After we get all the C's, plug in the C's in the expression of t, then we can determine the function t over each subinterval. So this function not polynomial. So in this example, we use a long polynomial function to do interpolation. Yeah, this is a tension spline. I just give you some idea how people use other functions to do interpolation. Yeah, this is one example. A second example is if the data is periodic. In those cases, people also don't use polynomial to do interpolation. Then what kind of functions people use to interpolate a periodic data set? Trigonometry functions. That is a second example. Yeah, second example. So polynomial interpolation is not unique. Yeah, this is a topic 1. I finished chapter 6 today. Then next, we turn to study chapter 7. Chapter 7. Okay. Chapter 7, topic 2. Yeah, chapter 7. Yeah. Chapter 7 is about numerically, not theoretically, numerically compute derivatives, usually first and second derivative, and also numerically compute an integral. But today, compute derivative first. We through Taylor expansions to compute derivatives. Okay. Topic 2. Topic number 2. Okay. Okay. First, we develop formulas, numerical formulas for first derivative. How to get first derivative numerically by Taylor expansion. Okay. Okay. Take a look. Okay. There are many formulas. Okay. Start from the simplest one. By Taylor expansion, we have x plus h. Expand this guy. First term, second term. Second term involves derivative. And the third term is error. The error is h squared over 2. Second derivative, evaluate at some point psi, where psi is between x and x plus h. Okay, now from this Taylor expansion, let me isolate the first derivative. Let me see. Let me move f of x to the left side and the error to the left side. Then divide the equation by h. Then we get derivative is equal to 1 over h. F of x plus h plus f of x. Then minus h over 2, second derivative. Now, I truncate this equation and drop the error term. Okay. Then we get derivative at x roughly is this. This is an approximation because I have dropped the error term. How good this approximation? The error. How about let me give a name to the error? I call it truncation error of this approximation is this. Truncation error, not round of error. This is not round of error. Okay. Truncation error because I truncate this equation to get this approximation. Okay. Yeah. First formula to compute derivative, and we call this formula an order one formula. Why order 1? Take a look at the power of h. When h approaches 0, error approaches 0. How fast? Order 1. The power is 1. Order 1 formula. We call this formula order 1 formula for derivative. First, formula to compute derivative. Second formula, in Taylor expansion, I use term 1, term 2, 2 terms. Now, one more term. I use one more term. Okay. B. Second formula. I expand this guy into Taylor series, but this time I use 3 terms. And then plus error. Error evaluate at some point, say psi 1, because I have a second, this is the first equation, I have a second equation. So psi 1, what is psi 1? Psi 1 between x and x plus h. Now, second equation, f of x minus h minus h derivative plus h squared over 2 minus h to the over 3 factorial. Psi 2, psi 2 between x and x plus h. Okay, now I subtract the second equation from the first equation. Then I cancel f of x. And also I cancel this term, the third term. Right? Then we get subtract from subtract the second equation from the first equation. Then we arrange the terms. Put derivative on the left side. Then we get this equation. Minus h squared. The derivative psi 1 plus the derivative psi 2. Okay. Okay. The error term contains psi 1 and psi 2. Actually, we can simplify the error term. Okay. Truncation error. Truncation error. Let me simplify it. Is equal to negative h squared 12 psi 1 plus psi 2. Divide the sum by 2. Then we get h 6 times 2. Let me draw a diagram. 0, x, y. Y is say the derivative, right? Psi 1. Here, psi 2 is between x and x minus h. Psi 1 is between x and x plus h. This is x. X minus h here. X plus h is here. Psi 1 is here. Psi 1. Psi 2 here. Psi 2 here. Suppose the graph of the third derivative is this graph. Okay, now third derivative at psi 2, say this point. The third derivative at psi 1 is this point. And the average of the third derivative at psi 1 at psi 2 is about here. Yeah, this is a f third derivative at psi 2. This is a f the third derivative at psi 1. So average is here. Take average. So average is here. So actually, between psi 1 and psi 2, there is a point. Let me call the point psi. The third derivative at this point psi is equal to the average. So I can simplify the error as the third derivative of the function at some point psi. What the point? Where psi is between psi 1 and psi 2. But psi 1 and psi 2 is between x minus h and x plus h. So psi is between x minus h and x plus h. So therefore, this equation, therefore, first derivative is equal to 1 over 2h times f minus the error. Now, I drop the error. Then we have a second formula to compute derivative, right? I drop, yeah. I drop the error. Yeah, we call the error truncation error, okay? Then we have a second formula. Roughly is equal to 1 over 2h f x plus h minus f x minus h. Or usually we write this quotient as this, yeah. Over 2h. Because the error, truncation error, is a square of h, right? Some number times square of h. Square usually is a small number. So we call the formula order 2 formula. Okay. We call this formula, this approximation, okay, an order 2 formula. An order 2 formula for derivative. Yeah, order 2 formula is more accurate than order 1 formula. Let me show you one example about this order 2 formula. So take a look. Example. Consider this function, arctangent of x. Okay. Then find derivative of the function and square root of 2. Yeah. square root of 2. Square root of 2. Yeah, take derivative on arctangent. It is 1 over 1 plus x squared, derivative of arctangent. Then plug in square root of 2. So exact value is 1 third. Okay, but now let me use this formula. Order 2 formula to compute this derivative. Then x is square root of 2. Now we need to pick an h. Okay, pick h. Let me make a table. Yeah. H. The first h is 1/4. 1/4 is 1 over 2 square. It is 0.25. If I choose h, 0.25, x is square root of 2. Then the derivative by this formula, by this quotient, is equal to 0.33719,385. If I choose h to be 2 to the third, what is 2 to the 10th? According to my notes, 2 to the 10th. Then this number is 0.9765 times 10 to negative 2, negative 3. Yeah. This h is quite small. Then I use this formula to compute derivative. I get 33.435. Yeah. The exact value is 1 third. 1 third is 0.3333, and so on. So when h is this number, the solution is quite good. But if I continue to decrease h, say 2 to 18, wow, this is a very small number. This is a 0.3815 times 10 to negative 5, very small number. Right, then if I still use this formula, then I get the answer is a 0.32. Yeah. So when h is too small, by this formula, the solution is worse. It's getting worse. Why? Because when h is too small, round of errors start to ruin your result. Round of errors start to dominate your computation. So, yeah, this solution is worse than this solution because of round of error. So h cannot be too small. This is today's class. Let me stop here.